Okay, Bismillah ar-Rahman ar-Rahim, wa salatu wa salamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. Okay, I'm very happy to provide the course on deep learning and neural network. Okay, so for the course, you have all the information on LMS. I posted the slides. So we have here the course syllabus that I'm going to present today. And I will be posting all the different resources, slides, labs in this page over here. So it's decomposed into topics. Today I'm going to provide an introduction about deep learning and then also an introduction about Python programming language because we'll be using Python during this course. So let me get started. So the course is CS489 about deep learning and neural network. So we will have the course during Sunday and Tuesday from 2 to 3:30 or 40 p.m. in the Robotics and Internet of Things lab facilities over here. Dr. Adel Ammar and also Mr. Bilal, they are here. They will be assisting us into the course, especially in practical assignments, labs, and so on. So whenever you need any help, you can consult them. They are expert into the practical side of neural network implementations, development, installation. You will be facing a lot of issues for the installation of framework and so on. So here you have full assistance from our colleagues. So basically we have three main outcomes. At the end, you will be able to apply neural network for deep learning applications. Deep learning applications are vast array applications, and there are different architectures of neural network. We are going to introduce how to use neural network, for example, for computer vision application, for text processing, for speech processing, for linear regression, for different kind of use cases. So at the end of the course, you will be able to know which neural network will be suitable for which kind of application. And second outcome is to recognize the concepts of deep learning. There are so many concepts related also to the machine learning. We are going to introduce this concept step by step. And the third CLO is to design deep learning architecture as well. So this is our course outline. Starting from today, we're going to make an introduction about the course, give some motivation to deep learning and what are the different categories of deep learning applications. We will also perform very simple image classification using the KNN algorithm. Then we will introduce the concept of neural network. Because neural network are used in a variety of applications and they are quite old technology, but I'm going to explain you why neural network have gained a lot of popularity in the last maybe 6 or 7 years. So you will learn about general concepts of neural network and then some advanced concepts about how to tune the parameters, the hyperparameters, regularization, optimization of the architecture. And you will learn how to structure machine learning projects. And then we go into the convolution neural network. So convolution neural network are a particular architecture that is applied for computer vision applications. Okay. Computer vision applications. It is based on the basic neural network, but it has also other layers that are called convolution that will allow actually to improve the classification accuracy in images, which is a very complex problem. It has been a very complex problem since several years ago until 2012, where this technology has found very accurate results as compared to the previous ones, and this is why it's getting more and more importance. We will talk about also deep convolutional models. Also, we will learn about object detection. You have an image that contains several objects. So you won't say that image classification, you say whether this image is for a cat or for a dog or for a car or whatever. But for image detection, you're going to detect the location of every object and then you classify it, which is a more complicated problem. Then you will learn about face recognition and one-shot learning, how the computer will be able to recognize the face. It can recognize people by their faces, okay? And then we will talk about sequence models. And here we will talk about recurrent neural networks applied to text recognition, speech recognition, and so on. Because the nature of the input data is different from images. So it is processed in a different way. There are other type of architecture that is called the recurrent neural network that you're going to learn about. And the two last topics are advanced topic about GANs, generative models. And GANs now are very popular. They allow actually to generate things that are very similar to reality, but they are fake. So you can generate a fake face, a fake object that does not exist, but when you look at it, you say that it's really very realistic. Okay, and it has a lot of applications in security, in computer vision, and different areas. And finally, detection and segmentation. So the course is very dense, but actually you will learn a lot. And the importance of this course is not like any other course. It is a course that will open the horizon for you for a big market. Now in Saudi Arabia or in the world, AI is almost the most important thing. Everybody now is talking about AI in any discipline. And even I believe that in the Saudi market there is little skills about advanced artificial intelligence engineers, especially in the computer vision area. So I think you are lucky now to have this course in order to get the ground, to get the basis. Later on you can join big tech companies that are looking for AI engineers, or even you can open your own company, because now it's kind of easy actually to make a startup using AI nowadays. So about the assessment, like the courses that I have taught in robotics or in Internet of Things, I don't like to make the traditional approach of assessment like written exams, stuff like that. We will have final exam, that is for sure, because this is per university regulations. But basically most of our assessments will be project-based, will be individual work, teamwork, okay? Because the objective is that you practice as much as possible and then you grasp the concept of deep learning as much as possible. And this is not through like a traditional way of assessment. So we will have a major exam. You will have different projects, different assignments, practical assignments, and of course at the end we will have a final exam. So this is the grade distribution. Basically you will have 20% for every type of assignment and 40% for the final exam. So let me get started with the course. Do you have any question? Okay, so let's start from this slide, because most of the lectures I'm going to present will be about computer vision. But I'm going also to give some other use cases, but the focus will be on computer vision. So first of all, we need to understand how do we see and how the camera is actually seeing. So basically the camera is nothing but emulating the human eye. Okay, so in the human eye we have the retina here, and then when it receives some lights, we're going to have a negative image in the retina, and then you will be able to see. So basically the same thing happens into the camera, which has also some lens, and the light is going to come through the lens, and finally you will have here a sensor, the film or the sensor, where the image is going to be captured. And then this image nowadays, because we are in the digital world, you have pixels, and every pixel would have a specific color. Now if we look at an image, it will have the following structure. It's like a two-dimensional array. Okay, it's a two-dimensional array of numbers. So for you as a human being, you can see that this is a cat. Okay, and if we focus at a certain part of the image or the whole image, basically it's going to be something similar to this one. They are numbers. So when you see these numbers, can you know that this is a cat? Obviously not. Okay, so the numbers are between 0 and 255, and you have also 3 different colors. You have 3 channels, one for red, and one for green, and one for blue. So when you superimpose all these different channels, you will have the colored image as you can see it here. But at the end, we will have an array of red colors, we will have an array of green colors, and an array of blue colors that will form the image. In the case of black and white or grayscale image, you will have only one array, and you will have values between 0 and 255. So 0 is dark, and 255 is white. Okay, and that's how it works. So same thing here. So an image at the end is a matrix of numbers, and you can clearly see from this example how difficult for a computer to know what is inside an image. It's really a very challenging problem, but nowadays, of course, we have plenty of solutions. But until maybe 10 years ago or even more, this problem was actually very challenging to know what's really inside an image. So I'm going to take you through different techniques that were proposed before the area of neural network. At least you can have an idea, and then we will see how neural network has actually changed this technology and provided very high accuracy of the image classification and detection. Yes, so each channel here, it will have a value between 0 and 255. Same thing here and same thing here. Why between 0 and 255? Because the color is encoded into 1 byte, and the byte, it takes the value between 0 and 255. Of course, computer vision is an old area, and a lot of problems were addressed by the research community. And one of the milestones is the face detection and not face recognition. So what's the difference between face detection and face recognition? So the face recognition, I'm able to know who you are, but for the face detection, I'm able to know that there is a face for whom we don't know. Okay? So face detection was actually devised in 2001 by Viola and Jones. These are two researchers that have come up with an algorithm that is able to detect face of humans. And they have used some different types of machine learning techniques in order to do that. And 4 years or 5 years after, it was implemented into mobile phones. So now if you take your mobile phone, it will be able actually to put a square on the different faces that are detected into an image. Okay, so basically they are based on this kind of technology. And in 2005, the computer vision community have come up with several data sets in order to provide challenges for the community and come up with solutions to object classification problems. So one of the first data sets is called the Pascal Visual Object Challenge, which we call Pascal Vak. And it's a collection of data sets for object detection, which provide a standardized image data set for object class recognition. And you can see here along the years from 2006 to 2012, the mean average precision reaches around 40%, which is not very good for image classification, but this was using the techniques prior to neural network. Okay, and there are so many other data sets that were proposed also in for the computer vision community. We have the CFAR10. I'm going to introduce you some of the most known data sets that nowadays are used as benchmark for computer vision application. So CFAR10, it's a data set that contains 60,000 images, and every image has 32 by 32 pixels. Okay, and it is divided into 10 classes. This is why we call it 10, CFAR10, because it has 10 classes: airplane, automobile, bird, cat, deer, dog, frog, horse, sheep, and truck. So the challenge is basically you have this data set, it's already labeled, and you try to come up with some algorithms that will try to identify the object inside the images. And the images were divided into 50,000 training images and 10,000 test images. So usually in machine learning, when you have a data set, you will decompose it into two main parts: one for the training and the second one for the testing. And usually the ratio is between 80% for training and 20% for testing. Of course, in very, very large scale data sets, so the percentages may change. We can go up to 95% of training and only 5% for testing. Now, depends on the scale and the number of images that are provided into the data set. So you can find this data set available in this link here. We have also the MMIS data set. This is very famous, and it's almost the hello world example for starting deep learning. It's a hand digit library or handwritten digits available. Okay, and it also contains 60,000 examples. 10,000 of them are for test, and the other 50,000 are for training. So it is used in order to recognize some hand digits automatically. We have also the fashion MMIS data set, which is another data set that contains different type of clothes. Okay, so it has also 10 categories for different type of clothes: t-shirt, trousers, pullover, dress, coat, and so on. And it is used another alternative for MNIST. So MNIST is like very classical, and this one is like MNIST. It has images 28 by 28 grayscale images associated with label from 10 classes. Okay, so it helps, for example, if you devised an algorithm for MNIST, you can try on another data set, because here the features are different from hand digits. And usually, in order to validate a neural network or any machine learning model, you need to run it over different data set to see. Maybe it works pretty much fine on this one, but not in the same way on others. There is also the Caltech 101. It contains 8,677 images, also for 10 categories, for 101 categories, not 10. So here we have much more categories, and in every category we have 40 to 800 images, and most of the categories they have 50 images for classification also. There is the Stanford car dataset. It contains 16,185 images of 196 class of cars. So it will detect the car, the brand, the type, the age, and so on. Okay, and I have seen even recent projects that did for a new dataset for recent cars. Okay, so this is a good question. Now, when we talk about deep learning, it's like we're talking also about machine learning. So in machine learning, usually what do we have? We don't have like known equations of a model, like you provide an input, you know what's the output according to some theoretical model. No. You have like a black box, which is initially random. And then what you will do, you're going to put data into this box, and you will tell for this data, it corresponds to this output. Okay, so this is what we call the training dataset. The training dataset allows you to develop your model more accurately. Okay, once you have developed your model accurately, it means that the error is very small for the model, for the training images. What you will do, you will try to see, okay, now I have optimized my model for the training dataset. Does it work on any other unseen object? So we need to bring some unseen objects. And these unseen objects must be labeled in order to compare between what the model is going to predict with respect to the ground truth, that is the correct label for the new data that is in the test. So that's why for every machine learning project, you need to have data, which is the most challenging part, because if you have the data, you've done maybe 80% of the work. Okay, and then you have to divide this data into two parts. I'm going to talk about this in more details during the lecture. One for the training, which help you to develop the model, and another one for the testing, which helps you to validate your model, to check whether your model is correct or not. Okay, so this is basically and of course, the objective of this course is actually to try to develop models based on this paradigm. Okay, so the big data set that considered nowadays as the main benchmark for computer vision algorithms is called the ImageNet. And the ImageNet is a very huge project from Stanford University, okay, that contains 22,000 categories, number of categories, and 40 million annotated images. So it's really a huge work. This is a very, very large database that is considered nowadays as the standard for validating computer vision algorithms. So for example, if you develop any new architecture for image classification, you need to compare yourself with others. So you will use the same data set, and then you can compare what the other have found with respect to your finding. Okay, so for the image classification that is called the ImageNet or the ILSVRC, the ImageNet Large Scale Visual Recognition Challenge, it consists of having 1,000 classes, so it's less number, and 1.4 million images, so almost 1/10 of the number of images. And the AI researcher Fei Li began working on this idea from 2006. I think also having the experience of building a data set is very important for AI engineers, because this is like the first step to start to know how to label the data and what is the impact of labeling later on the training. So if you want to get involved into the labeling task, we can also get you into some of our running projects on this. Okay, so this one was used as a benchmark to test between computer vision applications, and every year there was a competition that the researchers will come up with new algorithms and they will compare between them using the ImageNet dataset. So until 2012, I mean 2010, 11, and prior, the algorithms were not based on neural networks. They were based on different techniques, and the maximum performance that was obtained is around 75% of accuracy. Okay, it means here 25.8% of error. Okay, it means 25% is not going to give you the correct answer for the classification. Until 2012, we had the ImageNet network, which made a big achievement, so a big improvement. It reduces the error from 25.8 to 16.4. And here the community started to look more attentively to neural network. And then all the years after, the neural network was actually, the research community were designing different neural networks architecture. So here we have Zaylor and Fergus in 2013. Then we have VGG net in 2014, Google Net in 2014, ResNet afterwards. Okay, and the human error percentage is 5%. So here they were able to achieve 3.57, which is lower than human. It means they brought also some humans and they tried to classify the images by their eyes. And the humans were actually having 5% of error. So you can see now computer vision algorithms have greatly improved because of the use of neural network technology and different architecture come up. So we're going to learn about these technologies and the different architecture. In particular, when you will learn about convolution neural network. But before going to convolution, we need to understand what is a neural network and how it makes computation in order to make prediction, regression, or classification. So this is an overview about the different architectures that were proposed. So prior to 2012, it was based on classical machine learning algorithms. So here it uses some SVM and Hog techniques for computer vision in CVPR 2011. And then in 2012, this guy come up with the ImageNet architecture, and it takes an input as an image as input, and then it goes through different layers of convolution. So the convolution basically is going to reduce the dimension of the image. You start by an image, for example, 28 by 28, and it goes through different layers. Every layer is going to take like a summary. Some layer is going, for example, to make you the edges. Some other is going to take you some other features. So this is what we call the feature extraction. Usually, we try to extract some features. And for the image, it contains a lot of colors. But what are the most important colors that represent features? Okay, so in neural network, the feature extraction is done through some layers. And then at the end, when we extract all the features, we're going to compare these features with our database and check what is the most likely appearance of the image. So this is basically the idea here. And then after that, all the other works are based on this seminal work, that is ImageNet, and they have proposed different architecture with different depth, okay, with different convolution layers, with different filters, and so on. VGGNet from 2014 and MSRA in 2015. So now let's talk about some visual recognition problems. And this is important to know. When we work on computer vision, there are different problems, and we should not confuse between these problems. And every problem, it has its own solution. So the basic problem is called classification. What does it mean, classification? You have an image, and you need to tell what's the object in the image. In principle, you have only one object. So you don't need to localize, you don't need to do anything, but you say, okay, this image is for a cat. There is some background and so on, but this one is kind of noise. But what's appear here is a cat. And this is what we call image classification. Okay. The second problem is classification plus localization. You have one image, okay? So you don't tell that this image contains a cat, but you want to specify what is its position in the image. Okay, so here you have an additional information to provide, that is the location of the object. And how do we specify the location of the object? How do we specify the location of the object? using a bounding box. Okay, so, and this is what we do in labeling. When you have an image, you will make a bounding box. Of course, the bounding box is going to contain the image itself, but also will contain some background or some additional information about the image. So, and then the location will be the center of the bounding box. We will say that the object is located here. Okay, this is a more complex problem because we don't want to know only what's inside the image, but also the location of the object in the image. Another problem is called object detection. And here we have an image, but we have multiple objects. Okay, so we need to search for all possible objects and make a bounding box of them. So I will say that there is a dog in this position, there is a cat in this position, another cat here, another duck here, and so on. Okay, so this problem is, of course, more complicated because, first of all, we don't know what object we will have and where they are located. And there are different techniques in order to browse the image, okay, and then make different bounding boxes to find what is the box that likely contain one particular image. Another problem is called also instance segmentation. Okay, and here we don't make a bounding box, but we are going to make the boundary, the exact boundary of the object. And this is called segmentation. So you have classification and localization, object detection, and segmentation. Yes?
So I do something like this, and the image was like half of my face. Is it going to recognize everything or just?
Sorry?
If I take an image and do like this,
Yes.
is it going to consider my hand as same image or just my face?
Yeah, it depends on how you make the training. I mean, if you when you make the labeling, okay, so you will make labeling of different persons. Some persons will be doing like this, some person like this, some people walking, some people lying. So you will have to take all the different positions possible into your labeling. So later on, it will know, yes, from the feature. It depends on how you train your model in order to get the requested accuracy, of course. Now, for example, if you train your model only to recognize complete persons, if it finds half a person, it will not recognize. But if you consider a model that will take half person, fourth person, or occluded by something else, the algorithm, the model is going to be adapted to these new situations, and then we'll be able in the future to most likely detect this kind of objects. Yes?
Is the instance segmentation?
Okay, coming back to whether neural networks are new or not. So the works was from the 90s, as already mentioned, from Lukun and other authors. They have implemented neural network architecture, but at that time, the number of transistors in Pentium 2 was only 10 to the power of 6, and now they are at 10 to the power of 9. And they didn't have GPU, but nowadays we have GPU, and this is actually what makes completely different. Now, if you run your neural network onto a GPU, it's going to have a completely different performance if you run it on a CPU. So usually in CPU, it's completely useless, especially if your data is very high. Okay, it will, what takes years for a CPU, it can take few hours for a GPU. And also, the number of pixels used in training is much slower here than what we have in the ImageNet dataset. So with the advances of technology from 2012 and above, so we have now the needed hardware in order to run advanced and like computation intensive algorithm to like neural network in order to make better computer vision algorithms.